Today's goal is to compose functions algebraically. Algebraically meaning non-graphically, and identify inner and outer functions in a function composition. Let's take a look at our first example before we break down what the aim means. Given f of x is x cubed plus 12x squared plus 20x plus 24, evaluate f of 2. Keep in mind that when we say evaluate, the key is right in the word. A value is just a number. So f of 2 should just be some number. We can obtain that number by substituting 2 into x for the function. And then all we need to do from there is follow the order of operations to decide which operations to do first. Of course, we all know in PEMDAS we have to do parentheses first. The things in the parentheses, there's nothing really there to do. Next up is exponents. So we're going to have to square 2 before we multiply it by 12. And now we can finish any leftover multiplication. And then add up all our terms. You should get 120. Again, that's the value that we get when we evaluate f of 2. Okay, then the question asks, what are 2 times f of x? Well, this notation has 2 next to the function, which means we're just going to multiply 2 by the function. So we get 2 times the quantity, x cubed plus 12x squared plus 20x plus 24. And we can distribute that 2 to each of the terms. This time our answer is an expression. It's not a value. Okay, finally f of 2x. I noticed that f of 2x looks just like f of 2 in the sense that we're substituting something in for the value of x, but this time I'm substituting in an expression. So I have f of 2x equals 2x cubed plus 12 times 2x squared plus 20 times 2x plus 24. There's nowhere to substitute into that term 24. Okay, so again, using order of operations, I have 8x cubed. This time I had to multiply 2x by 2x by 2x to cube that term, plus 12 times 4x squared. When you multiply 2x by 2x, to square the 2x term, you get 4x squared, plus 40x plus 24. Make sure you're following order of operations. If you first multiplied the 12 and the 2 and then squared it, 12 times 2 is 24. 24 squared is a number much bigger than 48x squared, which is the term we'll get there. And then we'll finish simplifying. Notice that when I substitute in an expression, the result is another expression. Okay, so what you just did was substitution here, multiplication here, and substitution here, but because we substituted an expression, that's the same thing as function composition. Composition means that we are substituting an expression or a function into another function. So our goal today is to compose functions, that is, substitute functions and expressions into other functions, algebraically, meaning not graphically. And then if we're looking at a function, we can actually think of it as a function composition, a substitution, whereas you've got an inner function and an outer function. More on that in example 3. Okay, let's take a look at example 2. Given f of x, g of x, and h of x, find, and then we're given 3 different expressions. This expression is read f of g of x. I like to write my g of x smaller just to sort of emphasize. I'm going to take the entire function g and substitute it into the function f every time we see an x. Does this look familiar? It should. This is actually what we just did. No need to do the same work again twice. This is just showing that what we did up in example 1, where we substituted 2x into the function every single place where we saw an x, that's function composition. We can call that function f of g of x. Okay, let's take a look at the next example. This notation to me looks a little bit weirder, but it's read the same way. This is h of g of x, and the circle is really small. It's the same thing as this, h of g of x. If you see it typed, just like you see it here, the function names are the same size, but when I'm handwriting it, I like to put the inner function small so I can actually really visualize. I'm going to fine. I'm going to compose the functions h and g by substituting g into h. Okay, so I'm going to substitute 2x into this function every time where I see the function. So every time where I see an x. So sometimes I just like to write it out with little empty sets of parentheses so I can double check. Okay, yeah, this looks like the function h. And every time I see an x, instead of putting x, I'm going to put a 2x. And then I'm just going to follow the order of operations to simplify from there. Okay, so this is my function, h of g of x. Okay, let's look at this final expression here, h of x. This is interesting. You can actually substitute a function into itself. So I'm going to take this expression, 5x squared minus x plus 1, and substitute it into itself. It's a little weird. Here's a perfect example of where I really like to use, and this is just a personal strategy, you can use it or not, but I just like to use big empty sets of parentheses so I can just double check. Does this formatting look like the function h? Yeah, it's 5 times something squared minus something plus 1. And now in that something, I'm going to fill it in with 5x squared minus x plus 1. And then I'm actually going to choose to stop here. If the example said, write your answer in standard form, to square this term, I would need a gigantic box method, right? With 5x squared minus x plus 1 times 5x squared minus x plus 1. And then I'd still have to multiply by 5. I'd have to subtract all these terms and add 1, all of which you're very capable of doing. It's just kind of tedious. Since, let's go back to the question. It didn't ask me to express the functions in standard form, so this sort of unsimplified form is totally fine because it shows all I have to do is take the function h and put it inside itself. Okay, one more example today, and this is where we're going to identify inner and outer functions. This is a trick you're going to use in calculus a lot when you get to the chain rule. It's a derivative rule, all of which is going to mean a lot more to you next year. Okay, when I look at this function f of x equals the sine of 2x, what it's saying is I can think about this as a composition of one inner function sitting inside of an outer function, right? I can see that 2x is sitting inside of sine, and so I can say that this is the same thing as g of h of x if h of x, that inner function, is 2x, and the outer function, g of x, is the sine of x. Likewise, I can see the function x minus 3 sitting inside of this bigger rational piece. So I could call f the same thing as g of h of x if my inner function is x minus 3 and my outer function is 1 over x. This is the kind of thinking we've been doing all year when we think about transformations, right? When I look at sine of 2x, I know that sine looks like this, and all the 2 is doing is causing a vertical shrink, right? Which is going to change its period. It helps me relate two different functions, right? There are many different correct answers for these. For example, a really boring answer would be to say, okay, let's just call the inner function here h of x is just x, and the outer function is negative square root of x. This is true, but frankly, it's like not going to help you that much next year. So let's think of a slightly more interesting example. Maybe I think of the inner function as square root of x. And what I'm doing to that root is reflecting it, right? If I put this into x here, then you get negative square root of x, which is true. And in fact, I think of the square root of x as, here's our parent radical function, and when you reflect it across the x-axis, then it looks like this. You've been doing this idea of thinking about function transformations all year, so that in fact isn't that different. Okay, let's take a look at this next example. Again, there are different ways to do it. For me personally, I'm just sort of carving into the middle. I would say that my inner function is x plus 4, and my outer function, what am I doing to the x plus 4? Well, I'm squaring it, and then I'm also multiplying it by 3, right? I have to picture if this went here, would you get the original function? And as one more example, here, this one's a little trickier. There are different ways to do it. Maybe I want to think of this as the inner function h of x. And that would make the outer function, what am I doing to that? Well, I'm multiplying it by 4, and then I'm subtracting 1. Again, I sort of like to double check. If I substitute, that expression, 1/2 to the x power in for x in my outer function, then I multiply by 4 and subtract 1, then I do indeed end up with my original function.